Okay, today we're going to look at logarithmic functions. Logarithms are inverses of exponentials, so they are a nice follow-up after we talk about exponentials. We get into logarithms. Okay, so as an inverse of an exponential, there's a nice relationship between an exponential equation and a logarithmic equation. So here's like an exponential equation that we were working with yesterday. You would take something to a power, all right, and that power would be a variable. All right, so if you see it looking like that, we have a nice relationship that we can convert it into a logarithm, and logarithms just undo the exponential part of it. So if you look at it, now what is important to understand that a logarithm is really an exponent. And in this case, this logarithm right here is equal to y, because if you'll look down here, y is the exponent. So when I'm looking for a logarithm, I'm looking for the exponent that I would have to raise this value to. In this case, it's an a. So what value would I have to raise a to in order to get an x? Okay, as a logarithm, we write this as log base a of x equals y. And what that means is a is my base, and so I have to figure out what is the exponent that I need to raise it to in order to get this value x right here. So we kind of do this loop thing to help us remember that relationship. So this base a raised to this power should equal x. Okay, so let's try some of those. Let's just practice evaluating some logarithms. All right, so on this first one, I'm looking for log base 7 of 49. Now remember, the log is just the exponent that I have to raise 7 to get a 49. All right, so that one's not real tricky. I need to raise 7 to the second power. So log base 7 of 49 would be equal to 2. All right, let's try another one. Log base 2 of 8. So 2 to some power would get me an 8. Okay, and so that power should be a 3. All right, let's get some trickier ones. How about this one with a radical? 5 raised to some power should equal a square root of 5. All right, that should take you back to your Algebra 2 days. When you take the square root of something, that is the same thing as taking it to the 1/2 power. That's something that you're going to need to remember, that if you have the square root of 5, that's the equivalent of 5 to the 1/2 power. If I was going to cube root something, and I'll say 5, it's not going to cube root nicely, but that would be the same as saying 5 to the 1/3 power, or fourth root would be a 1/4 power. So in this case, 5 to the 1/2 would be this, give me a square root of 5. All right, on this next one, 7 raised to some power would get me a 1. Well, anything to the 0 power would equal 1, so any base would work for that. If I'm taking the log of 1, I should get 0. All right, and this last one here, log base 4 of 0.25, we're getting gradually harder. That's kind of weird because it's a decimal. So what I would probably do is I would look at that as a fraction, actually. Let's look at it as a log base 4 of 1/4. Let's see if that helps. So now I have to figure out what power to raise 4 to get a 1/4. Well, 4 to the first power gets me a 4, and if you'll recall, to bump that to the denominator, you have to make it a negative value. So that would be equal to a -1. If it was a 1/16, it would be a -2. Okay, why don't you take a minute and pause the video. We did a little quiz on our clickers in class, but try doing these on your own. See if you can evaluate the log. Find the exponent that you have to raise that base to get your number. Pause the video and then come back. Okay, let's go through these. I'm just going to go pretty quickly. 6 raised to the second power would get me a 36. So this would be equal to 2. 2 raised to the fourth power is equal to a 16. On this next one, 4 squared, this is the one I had done earlier, 4 squared gets me the 16, but to bump it to the denominator so it's a 1/16, I have to make it negative. So it'd be a negative 2. Anytime I'm square rooting, so that would be a 1/2 power. The log of 1, regardless of this base, anything to the 0 power is equal to 1. All right, on number 6, here's another one of these fraction ones. So the first thing I have to do is figure out 2 to what power would get me a 32, and that would be to the 5th power. And then in order to bump it to the denominator, I've got to make it negative. So it should be a negative 5. All right, this next one, 10 to what power is 10,000? That would be to the 4th power. And last one, 3 to some power gets me a square root of 3. Again, anytime you're square rooting, you should have a 1/2 power. All right, hopefully you did well on that. Let's go ahead and move on. There are a couple types of logarithms that are special, and so let's talk about those before we get too far here. One type is common log. Okay, a common log is exactly what it says. It's a logarithm that we use a lot, and it's a base 10. Now we've been doing log base a lot of things, but a base 10 is so common that we look for a shortcut for it. So instead of writing something like log base 10 of 7 like this, as we do this more and more, we'll stop writing this 10 right here, and it'll look just like this, log 7. So anytime you see a logarithm without a little base, we assume it to be common log and assume that that base is 10. Now this is the only logarithm, well it's not the only one, but it's the main logarithm that you have a button for on your calculator. So you might take a minute and look at your calculator because you're going to need that. Pause the video if you need to. You will see your log button, well depending on your calculator, it's probably over there on the left somewhere and it just says log. And let's try using it a little bit. Let's practice. Let's start with our mental math first though. If I have a log base 10, think of this as a base 10 of 100. So that's 10 to some power gets me a 100. That should be a 2. So type that in your calculator and see if you get 2. You just press your log button and then 100. All right, on the next one we have log of 1. Okay, so assume there's a little 10 here. We don't write it, but we assume it's there. So that'd be 10 to the 0 power, and you can type that in your calculator to check it. This last one doesn't come out so nice. 4,000 is not a perfect power of 10, so this isn't going to work great. But I guess what I would have you do is just maybe, I know we can type it in our calculator, and we will, but I want you to just do a little bit of mental math and think through if it was a log base 10 of 1,000, well that would be a 3, and if it was a log base 10 of 10,000, it would be a 4. So since 4,000 falls in between there somewhere, when you press this in your calculator, log 4,000, you should get something between 3 and 4. You can check it. Okay, the other special type of logarithm is a natural log. It's a log base e. So if you recall from yesterday that e is approximately it's approximately 2.718. So when we have a log and we want to have a base e, or a base 2.718, we think of it like this, but that's actually not how we write it. Again, it has its own special notation, and it looks like this. It's ln, I don't know why it's backwards, but it's ln for natural log of x. So you don't actually write the little e for the base, and this ln, this is kind of how it looks like in textbooks, but it also kind of looks a lot like a 1n, and so I'd rather you use either a capital ln, like this, and you actually can find that button on your calculator. They'll use a capital ln, or you can use a cursive ln like this. That would work as well, but let's try to avoid using something that looks like 1n here. So this button is the other logarithm button that you have on your calculator, so you can also evaluate natural logs. and you'll just have to find it. It's actually, yesterday we were using that E button, but it was second ln. Okay, so ln is what the button you want now. Okay, let's try a couple of these. So this first one, and this is supposed to be really easy, but it always throws people off. Don't overthink it. We have natural log of e to the 5th. So anytime you have a natural log, you have to imagine there's a little e right here. And so you're saying e to some power is equal to e to the 5th power. Let me write that out so you see what I'm saying. E to some power has to be the same as e to the 5th power. Well, this power is going to have to be a 5. So don't overthink that. E to the 5th power is e to the 5th. And that's about where we stop. After that, since e is not a very pretty number, these don't come out nice. These aren't typically going to be mental math ones. And so it would just be something you'd type in your calculator. You could use your natural log button and type in natural log of 15 or natural log of 64. Or try this one. Do a natural log of, and it should open up parentheses for you, of -6. And you should get some sort of an error message in your calculator, because we actually can't take logs of negative numbers, and that was something I kind of breezed over on a previous slide, but you do have some restrictions, and you can't take the log of a negative number. Alright, so those are the special logs, common log, natural log. Beyond that, we're just going to kind of practice today doing some switching between these two forms. This leads us into what we're going to be doing futuristically, which is going to be solving some equations that have some logs or have some exponentials in them. So since these are inverse operations, we need to be able to switch back and forth between the two forms so that we will futuristically be able to solve. So today we're just practicing switching forms. So on this first one, let's do this first column right here. Let's switch these logs into exponentials. And this is just the big loop thing. So it's just 5 to the 9th power equals x. So you should write 5 to the 9th power equals x. On this second one, you have to imagine there's a little e here. And so then you do the loop. E to the 32nd power equals x. All right, you do this last one. Switch that one to an exponential. All right, you should have written 3 to the x power equals 9. All right, so once you get the hang of doing that loop and switching to that form, let's also talk about how do you switch the other direction. Okay, so now this is an exponential, and I want to turn it into a logarithm. So you have to kind of pay attention to the relationship between everything. Remember that the logarithm actually just is an exponent, so it will always equal the exponent. So you can see here it equals 9, because 9 is my exponent. The base of the logarithm is the same as the base of the exponential. Remember, this is your base, this is your exponent. Okay, so let's see if we can set these up. So in this one, it's a base 4. So I should be doing log base 4 of 64 should equal my exponent. So it will equal x. And you can always check that with your little loop. 4 to the x equals 64. Or if it helps you, you can just do the loop backwards, and so you can say log base 4 of 64 equals x. You can do that also. Okay, I just always kind of remember it's got to equal my exponent. So on this one, it's log. This time the base is x, so make your base little. Of 39, make the 39 big, equals my exponent. You try the last one. All right, I'm going to guess that you got log base e of x equals your exponent. Okay, which is okay but not ideal, because remember that we don't really write base e. Instead, we change this log base e into a natural log of x equals 6. That would have been a better answer there. Get rid of the e eventually and just call it natural log. Okay, so in class we kind of practice this a bunch, and it's going to be something that takes a little bit getting used to switching those forms. You can ask me for a worksheet. I can give you a practice worksheet if you want one. Okay, so then the other thing that we're going to talk about today are the graphs of logarithms. Now there's different ways to graph these, but I like this relationship that it has with an exponential, because the exponentials are something we're a little bit more familiar with. And so we'll probably start by graphing the exponential and then look at the relationship that it has. Okay, so let's start with the exponential. The parent graph yesterday was y equals 2 to the x. Let's throw in some ordered pairs. If you have a negative 1 for x, you'd get a 1/2. If you plugged in 0, you'd get 1. 1, 2 to the first power is 2. If I put in a 2, 2 to the second power is 4. Put in a 3 for my x. 2 to the third power is 8. Okay, and so those are all some nice points, and you can kind of see them plotted over here. Here's my over 0 up 1, over 1 up 2, over 3 up 8, or I'm sorry, over 2 up 4, 3, 8. Those are all nice ordered pairs that land on that graph. That's what we did yesterday, and we had this horizontal asymptote. Okay, so that was yesterday. Today we're going to graph the logarithm. Now because logarithms are inverses of exponentials, you'll notice that these two graphs reflect nicely over the y equals x line. And if you will also recall that inverses, as far as their table is concerned, their ordered pairs swap. So this negative 1, 1/2 that I have here is going to turn into a 1/2 negative 1. So over 1/2 down 1, which is about this point right here. Okay, let's try again. The next ordered pair is 0, 1. So I'm going to change that to a 1, 0, and I'm going to plot it right there. And then my 1, 2 turns into a 2, 1. Over 2 up 1. Yeah, you can see these plotting nicely on this graph. 2, 4 turns into 4, 2. And 3, 8 turns into 8, 3. And so you can see all of these nice points that fall on that graph that are just reflections of the exponential. The other thing to notice is that on the exponential we had a horizontal asymptote. Well, on the vertical, or on the logarithm, you're going to have a vertical asymptote right here on the y-axis. So this should come down and approach that. So instead of shooting up very quickly like an exponential does, a logarithm shoots over to the side very quickly. Okay, so let's just look at some, because not all of them are base 2 as soon as you change the base on it. Okay, so if you look at this, a y equals 3 to the x. If I plug in a 1 for x, I get a 3 for y. There's my ordered pair. If I plug in a 2 for x, I get a 9. Oops, not there. If you were to swap those ordered pairs, instead of going over 1 up 3, I'd be going over 3 up 1. There's that point. Instead of over 2 up 10, I'm going to go over 10 up 2. And you can see how those lie on there. So that's kind of a handy realization to know that those ordered pairs are just going to flip-flop. So let's practice graphing some on our own. Alright, so the first thing on this one I want you to notice is the 5 out in front. So think of that as your A value. That's going to be a vertical stretch. So we'll come back to that later on. Let's start by graphing this log base 4 of x. To graph a log base 4 of x, I kind of like to think of it as an exponential with a base 4. So think of it like what we did yesterday, a base 4. And let's make up a quick little table. If I plug in a negative 1, I'd have a 1/4. If I plug in a 0, I'd have 1, 1, 4. And if I plug in a 2, I'm already way off my graph. And that typically happens. There's really not a lot of points to plot on these because they get big pretty fast. Now, if I want to graph the logarithm, so this is log base 4 of x, not worried about the 5 yet, just do a log base 4. Well, all that is the flip-flop of the 4 to the x. So instead of a negative 1/4, I'll put my 1/4, then my negative 1. And change my 0, 1 to a 1, 0. And so you just switch all of the x's and y's. Let's go graph the, oh wait, I'm sorry. Before we graph those, let's talk about that 5. Remember that that a value means that your y's are all 5 times what they normally would be. So I'm going to take this column right here and take it times 5. So this 1 is now a 5, and this 0, well, 0 times 5 is still 0. And I'm sorry, I missed my little negative I had on that. That's a negative 5. And then this would be a positive 5, and this would be a positive 10. So let's go plot these points then. So the first one says go over a 4th and down 5. So here's my new point. The next one is over 1 up 0. That's kind of that key point that I kind of called the vertex. It's not really a vertex, but on the exponential, it was right here. On the logarithm, it's on the x-axis. Okay, let's go back to graphing. So over 4, up 5. Okay, that's way up there. That's that vertical stretch happening. And the last one, over 16, up 10. That's way off my graph over here someplace. All right, so your vertical asymptote didn't change. It's still right down the middle. And then you have your graph come up here. And it helps if you remember that these log graphs just kind of shoot off to the right, like that one. All right, that's not so bad. That's a logarithm. You always graph the exponential first, then flip-flop it, and do any transformations that you need to do. Let's try one more. Okay, so this one is a common log because there's nothing there, so we assume that that's a base 10. So we start off and we graph the exponential that's a base 10. So 10 to the x. So if I put in a negative 1, I should get 1/10. If I plug in a 0, I should get 1. Plug in 1, I get 10. And then pretty much I'm off my graph. If I put in a 2, I'm at 100. So that's way too far. Okay, so then what I'm going to do is I'm going to flip-flop all of those x's and y's. So then I'll have my log base 10 of x. So 1, 0, and 10, 1. Okay, now there's a couple ways to do this. You could just go plot those and then do all of your transformations. This negative here is going to reflect it over the x-axis. It's kind of like on a parabola. When you have a negative out in front, it flips it upside down. So that will flip it over the x-axis. And then this minus 3 is out at the end, so that's going to take it down 3. Now, as a quick little side note, if you had this in parentheses, and sometimes you will, now that's grouped with the x, and it's a left and right movement, so that would move it right 3 if it's caught up in parentheses. But this one's not. The negative 3 was loose out there, so that's my up and down movement. So I'm going to reflection, and I'm going to shifting down 3. So different ways to do that. I think what I'm going to try here, something I think might be easier for you, is that this negative 1 that this negative that we have right here is like having a great big negative 1 instead of that 5 on the first example. It's like having a negative 1 there. So let's just take all of these times negative 1. And what that's going to do is that's going to take care of my reflection for me. Okay, so now I'm going to go ahead and just do that much. Let's just start there. So my first ordered pair is going to be over 1/10 up 1. And the next one is over 1 up 0. And the last one is over 10 down 1. So you can kind of see from that, there's not very many points, but a normal logarithm would shoot off to the side. And what this one did, since it reflected over the x-axis here, Now this one is shooting off underneath like that. So let's go ahead and graph that. It comes down and crosses those 2 points. And then you didn't move it left and right yet, so or at all, and so you still have a vertical asymptote. Okay, and then the other thing that I want to do, okay, I got to do it. Sorry, I got to clean that up. I really shouldn't have dipped so low there. Let me more like that. Okay, and so that is the first step. That's the reflection, but I still have to move this thing down 3. So I would take all those points I plotted and move them all down 3. And then graph the line. Okay, and your vertical asymptote, we didn't move left and right at all, so it's still going to be right here on the axis. And that is the graph of that logarithm. Okay, they take a little bit of time because you got to first start with your exponential and then do some transformations maybe when you're done. So you should have a few graphs for your assignment like this. All right, last thing I wanted to try like a word problem type of thing that has a logarithm in it. And so this one says a drug is administered intravenously for pain. And so this function, which is kind of a messy function here, models the amount of the drug in the body after t hours. So I'm going to put in my hours here, and this f of t is the amount of drug that's still in my system. Okay, you might notice that my time goes from 0 to 24, which kind of makes sense. It probably is within a day how much is still left in my system. Okay, so let's answer a few questions. It says, what was the initial number of units of drug administered? Okay, so that says when t is equal to 0. So you can plug 0 in for t, which would go right here, which means you'd be doing the natural log of 1 plus 0, or 1. And remember that the log of base anything of 1 is going to have to be a 0. So even though this is an e, I'm saying e to what power gets me a 1. So this whole thing right here ends up being a 0. Times the 23 is still 0. And so we end up in the end with an 80 minus 0, which is just an 80. Okay, so that's my initial number of units, 80 units. How much is present after 2 hours? Okay, well that becomes a calculator problem then. What you're going to do is you're going to plug a 2 in for t in this equation. And so what that's going to end up being is a natural log of 3. When you plug a 2 in for your t. Okay, so if you go to your calculator, and you're just going to take 80 minus 23 times the natural log of 3. And you should get 54.7, which seems kind of reasonable. I had 80 units to start with, and then it starts to wear off, so it should be less than 80. So 54.7 units is what's left. Okay, and then the last thing says draw the graph. I didn't really leave myself any space, and I'm not looking for this to be exact. I just kind of like you to see kind of what's going on with this function. It looks like it's a mess of a formula, but look at this. I really could kind of rearrange some things and put this 80 that's on the front that they sometimes like to do. Let's put that on the back end. So I have a negative 23 natural log of, I'm going to switch this around and call it t plus 1. And then I'm going to do my plus 80 out at the end. And when you see it like this, you should start to notice, oh, those are just transformations. So I would take my regular parent graph, which kind of looks like this, and from that, I would have to reflect it over the x-axis. I'd have to stretch it by a factor of 23. I'd have to move it left 1, and I'd have to move it up 80. And all of that could just transform the parent graph. Okay, so just something to think about. We're not going to have to actually graph any that are that tricky, but I want you to see all those parts that we've done with parabolas and with rationals and everything still work with logarithms. All right, hope this helps. Good luck.